There is a growing understanding that the observable universe is far more intricate than the basic models once suggested. Beyond the familiar images of galaxies, nebulae, and the quiet interstellar medium lie processes that for decades remained in the shadows, hidden not only by the limits of our instruments, but also by the limits of interpretation itself. Tonight, as you slowly drift toward rest, we will gently walk through these lesser-known layers of the cosmic architecture, layers that shape the large-scale dynamics of the universe, influence the evolution of star systems, and quietly guide the distribution of matter across unimaginable distances. Far out in the outer regions of intergalactic space, researchers have discovered elongated strands of matter, stretching across distances so vast that no ordinary observation could reveal them. These structures are known as the cosmic, Weber delicate skeleton of the universe, a silent framework upon which galaxies and clusters gently rest. The web itself is woven from incredibly rarefied gas, scattered so unevenly that only highly specialized techniques allow us to glimpse its presence. And within these threads, there are pocket places where density rises ever so slightly above the cosmic average. These pockets may ignite processes that shape the birth of galaxies. And some astronomers even whisper that these regions could give rise to unusually rare types of stellar systems. Although the cosmic web behaves under the broad rules of gravity, subtle irregularities appear anomalies that don't always match theoretical predictions. In some regions, astronomers detect accelerations with no visible mass to drive them. These silent deviations have inspired bold ideas suggesting that hidden components of the universe may be interacting with the web, components we still cannot observe directly. Among the most widespread hypotheses is the notion that these diffuse regions may be interacting with dark matter, an unseen substance, shaping the movement of gas and the distribution of energy across the filaments. Simulations reveal something even more mesmerizing: slow-moving pressure waves that ripple along these cosmic strands. Waves so vast that they span distances comparable to entire clusters of galaxies. If such waves truly exist, they may serve as a stabilizing, breath-maintaining balance between dense and rarefied regions, gently supporting the structure of the web across billions of years. Occasionally, scientists discover places where these filaments appear inexplicably empty. These regions are known as cosmic voids, immense volumes of space containing far fewer galaxies than their surroundings. Some voids are larger than the distances between the greatest clusters of galaxies we know. Their nature remains elusive. Some theories propose they were shaped by interactions between matter and fundamental fields during the universe's earliest expansion. What we do know is that voids are surprisingly stable, maintaining their boundaries even as nearby structures slowly evolve. Studying them may reveal how energy was spread immediately after the Big Bang. Certain models even suggest that voids can amplify or dim the cosmic radiation passing through them. A quintessence allergist, quiet portals through which ancient light drifts. Another fascinating mystery is the behavior of the intergalactic medium, the tenuous substance linking the universe's largest structures. Within it, particles travel at speeds close to the maximum possible, Launched by diverse processes, the powerful activity of supermassive black holes, the heating of gas between galaxy clusters, and perhaps more mechanisms yet unknown. These high-energy streams hold enough power to influence the birth of new stars, altering the chemistry of gas clouds as they pass, sometimes accelerating, sometimes slowing the processes that lead to stellar formation. A particularly important topic is the interaction between galaxies and intergalactic plasma. This plasma, existing between clusters, sometimes reaches temperatures far higher than anything observed in ordinary stellar systems. Such temperatures arise through gravitational compression and collisions of high-energy particles. The density and temperature of this plasma may affect how quickly galaxies cool and thus influence the pace of their cosmic evolution. Some theories speak of hidden flows of energy moving through the grand cosmic structures. According to these ideas, these flows may represent the transfer of energy through unknown components of the universe, components that defy direct detection. If such flows are real, they might explain the observed acceleration in the universe's expansion. Yet, for now, the evidence remains too delicate, too incomplete. There are also unusual galaxy clusters where mass appears distributed in unexpected ways. Their gravitational influence far exceeds what the visible matter can explain. This leads to the hypothesis that some regions might contain pockets of exceptionally dense dark matter. Calculations suggest that such environments might trigger the early formation of supermassive black holes, shaping the galaxies that grow around them. Another subtle mystery lies in how these vast structures interact with the cosmic microwave background, the faint afterglow of the universe's first moments. In certain areas, scientists observe slight deviations visible only through advanced data processing. But these deviations reveal how energy was spread billions of years ago. They hint that massive structures could have influenced the universe even before galaxies began to form. Enfin, some of the most delicate processes involve the intergalactic gas itself, gas that may exist not in one, but in several states at once. There are regions where hot gas maintains remarkable stability, held together by its interaction with ancient magnetic fields, resisting collapse even under extreme temperatures. These hidden processes, these quiet cosmic secrets, gently reshape our understanding of the universe, whispering to us that the cosmos is deeper, softer, and more mysterious than we ever imagined. It is believed that the magnetic fields of the universe's largest structures can gently guide the motion of charged particles, subtly redirecting entire streams of energy drifting through space. Some researchers even suggest that these grand, large-scale magnetic fields may have formed long before the first stars were born. And if that is true, then these ancient fields may have shaped the distribution of matter during the earliest chapters of cosmic evolution, at a time when the universe was still warm, expanding, and full of primordial motion. Despite the limited data, calculations hint that these early magnetic fields might have been strong enough to gently alter the trajectories of matter as it expanded outward during the universe's first breaths. Observations reveal that some cosmic structures move with unusually high velocities, velocities that cannot be fully explained by local interactions alone. It is suspected that these motions may be influenced by ultra-large-scale structures entities so vast and so subtle that we have not yet found a clear way to describe them. There are regions where galaxies appear to accelerate more than expected, as if responding to invisible gravitational tides. These mysterious motions may be the result of enormous gravitational anomalies, shaped across cosmic distances and unfolding over unimaginable timescales. The internal structure of stellar systems is also far more diverse than traditional models suggest. Even after countless studies, many processes remain unfamiliar to most people, though they may quietly determine the dynamics and behavior not only of individual stars, but of entire planetary systems around them. These hidden processes show themselves through strange variations in starlight, uneven flows of matter, unusual orbital arrangements, and delicate patterns of stellar interaction that resist explanation by standard theories. Within many stars, astronomers observe deviations that do not fit into usual evolutionary scenarios. For example, there exists a group of stars whose brightness follows cycles unlike anything caused by rotation or pulsation. These mysterious patterns may reflect processes unfolding deep within the star, perhaps irregular mixing of plasma, or intricate interactions with internal magnetic currents following winding, unpredictable paths. Because these processes unfold so slowly, decades of continuous observation are required just to trace the beginning of their rhythm. If such interactions occur, they would naturally alter the chemical composition of a star's outer layers, giving rise to unusual spectral signatures. This hypothesis remains unconfirmed, but observations reveal that some stars possess characteristics too strange to be explained by internal mechanics alone. Another area of interest involves stars that rotate unevenly. In some of them, the utterly creating complex magnetic patterns that twist and weave like threads. These magnetic lines can influence the flow of matter, forming localized zones of heightened radiation, patches of brightness that expand, contract, or drift across the stellar surface. Some researchers propose that such behavior may be caused by the gravitational pull of an invisible companion, perhaps a small black hole or a dense stellar remnant that leaves no direct trace in light. There are also stars that release unusual bursts of energy, brief, irregular surges detectable only within narrow bands of the electromagnetic spectrum. These bursts occur without noticeable changes in the star's other emissions, making them exceptionally difficult to identify. One hypothesis suggests that such events arise from interactions between deep layers of plasma and hidden magnetic structures buried far beneath the surface. Some stellar systems host extraordinary companions. In certain cases, exoplanets orbit their stars at steep angles so sharply tilted that it seems clear they were not born alongside their star, but captured long afterward. If such scenarios are true, they explain the unusual atmospheres and chemical compositions of these planets. Captured worlds often follow elongated, stretched-out elliptical paths, sometimes drifting so close to their star that their atmospheres begin to evaporate into space. Such planets are known as evaporating worlds, and studying them allows scientists to understand how stellar radiation shapes the fragile envelopes of distant planets. Certain binary stars also display puzzling behavior. In these systems, one star may slowly feed material into the other, forming dense accretion, disk-swirling structures with regions that rotate at different speeds. These differences create waves of density, which can become sources of high-energy radiation. These jets can stretch across distances equal to several light-years, glowing faintly as they pierce the interstellar darkness. There are also stars that appear to be influenced by external magnetic fields generated either by a nearby object or by the interstellar environment itself. When such a field is strong enough, it can alter the distribution of matter in the star's atmosphere, creating zones where the temperature or density dips lower or rises higher. These delicate zones shimmer and shift like soft patches of shadow and light, giving each star a unique and quiet signature written upon its surface. Such anomalous zones can gently alter the character of a star's radiation, creating unique and delicate spectral features like quiet signatures of hidden processes. Some stellar systems also possess orbital patterns that refuse to follow the usual formulas of evolution. In these systems, planets may drift along paths that slowly change over time, as if responding to an unseen rhythm. One hypothesis suggests that these shifting trajectories may be caused by a hidden object, something too dim or too cold to be detected directly. Such an object might leave no light behind, yet its gravity could still gently tug on the system, subtly shaping its motion. In rare observations, astronomers have found stars surrounded by the debris of destroyed worlds. When a star consumes a planet or a large asteroid, unusual chemical elements may appear in its spectrum, elements rarely found in ordinary stellar atmospheres. There are also hypotheses about stellar systems where the orientation of magnetic fields shifts periodically. These cycles may influence the stability of energy flows rising from the star's interior. If such magnetic changes occur regularly, they may produce characteristic fluctuations in brightness patterns that observers have recorded but still cannot fully explain, since only a few such systems have ever been identified. Some stars possess unusually large coronas, their outer atmospheric layers. In these coronas, temperatures can soar far beyond temperature of the star's visible surface. This is difficult to explain with traditional models because heat should radiate outward from the core, not intensify in the outermost layers. One hypothesis proposes that the corona is heated by magnetic waves traveling along magnetic field lines. Waves that gently carry energy upward, warming the thin, distant edges of the star until they glow with unexpected heat. There are also subtle processes known as hidden oscillations, vibrations deep within a star that rarely show themselves on the surface. Yet, these gentle internal waves may shift plasma structures and alter the distribution of energy. Studying them requires decades of spectral observations, watching for tiny changes that ripple slowly through time. Occasionally, astronomers discover stars with unusual shapes. Instead of perfect spheres, they appear slightly stretched or flattened. Such deformations may arise from rapid rotation or the gravitational pull of a companion object. In some systems, these distortions create uneven brightness, giving the star an appearance that feels strange, almost sculpted by invisible hands. The structure and evolution of galaxies involve countless processes that long remained on the fringes of scientific attention. But modern observational techniques now reveal phenomena once hidden by limitations in instrumentation or the absence of long-term monitoring. These findings not only enrich existing models, they demand profound revision. Many little-known processes in galactic evolution offer essential clues to understanding the mechanisms that shape the universe's largest structures. In the outer regions of galaxies, flows of gas drift along paths different from the typical rotation of the disk. These flows often stretch like elongated bridges or spiral arches connecting distant galactic arms. It is believed that such formations may arise from the influence of dark matter, its gravity forming localized anomalies that guide the motion of gas. In some cases, bridges or channels gently funnel gas toward the galaxy's core, stimulating new star formation. Studies also show that galaxies can experience faint mechanical oscillations caused by interactions with the intergalactic medium. When a galaxy passes through a region rich in gas, its disk may tremble ever so slightly, redistributing matter. These subtle shifts can trigger the formation of spiral arms not from internal rotation alone, but from external influences shaping waves of density that travel across the disk. Some galaxies possess unusual halos, vast outer regions made of gas, stars, and dark matter. These halos can be far more expansive than standard models predict. Observations reveal that halos contain large amounts of matter that do not form stars but do significantly affect the galaxy's gravitational dynamics. In certain cases, halos may even rotate independently from the disk, creating a complex interplay of gravitational forces. Some hypotheses suggest that halos may interact with intergalactic streams of energy. If such streams truly exist, they might influence temperature distribution in the halo, creating zones where cooling occurs faster or slower than expected. Gas may accumulate in these regions, eventually drifting toward the disk to ignite new waves of star formation. Observations indicate that in the central regions of some galaxies, certain structures, rings of gas, or dense clusters of stars may periodically change their orientation. These changes might result from external streams of gas or interactions with smaller companion galaxies. When such reorientations occur repeatedly, they can alter the activity of the galaxy's core, creating cycles of brightening and quieting. Another fascinating phenomenon is galaxies with asymmetric arms. In such systems, one arm may appear far brighter or denser than the other. This may be caused by the passage of a small object through the galaxy's disk, creating local disturbances that persist for millions of years, forming dense regions that eventually give birth to new stars. Some galaxies also contain unusually massive central black holes objects whose mass exceeds what would normally be expected for their size. These enormous black holes can influence star formation, heating nearby gas or ejecting it out of the central region entirely. In some cases, these low reach spanning tens of thousands, shaping the galaxy's evolution across cosmic time. Such cosmic processes can suppress the birth of new stars for astonishingly long periods of time. And in this quiet, almost imperceptible battle for balance, another force emerges: jets, thin but powerful streams of high-energy plasma launched from the hearts of galaxies. Although jets are widely known and often pictured in astronomy textbooks, their true influence on galactic structure is still underestimated. These radiant streams can collide with the interstellar medium, creating shock waves that shift the density of drifting gas. Sometimes, a jet can cause the whole galactic disk to tremble ever so slightly. A cosmic shiver that gives birth to new patterns, new currents, even new bridges of matter. Some galaxies reveal another mystery: stars moving along strange, almost rebellious trajectories. These paths sometimes contradict the rotation of the main disk. Sometimes, a passing galaxy, not even a full collision, is enough to create complex spiral patterns. These patterns can persist for millions of years, becoming nurseries for newborn star clusters. Some galaxies hide a peculiar phenomenon, counter-rotating core, where the central region spins in the opposite direction of the disk. This suggests an ancient union, a merger of systems with different chemical histories. If such events truly occurred, they may explain unusual galactic shapes and the strange compositions observed in their centers. Streams of gas may form where two halos brush against each other, transferring material from one galaxy to another like a whisper exchanged in the dark. Observations reveal that galaxies experience uneven pressure from the intergalactic medium. Some regions cool much faster, becoming cradles for dense clouds, the seeds of future stars. These ghost-like systems are difficult to detect, yet they may hold the key to understanding how mass is truly distributed across the universe. These appear when flows of external gas collide gently with the disk, forming pockets of density that may later become cradles of star formation. Another subtle question arises. Sometimes the central regions accumulate high-temperature gas, creating conditions where such giants can form. These stars, in turn, shape the future of the galaxy with their powerful winds and energetic radiation. The interstellar medium, too, is far from simple. What appears to be a smooth cloud is, upon closer examination, a tapestry of turbulent motions. Magnetic nuts, localized bursts of energy, and shifting densities. These interstellar clouds, made of gas, dust, molecules, and plasma, are dynamic, breathing entities. But star formation is not a gentle, uniform contraction. Some studies show that magnetic fields play a far larger role than once believed. These invisible pockets of force can hold gas in place, slowing its motion, and quietly increasing the chances that dense condensations will form. This separation may be caused by subtle processes that drift dust grains away from the gaseous medium. If these processes truly occur, they could create delicate, favorable conditions for the birth of planetary cores. Dust particles begin to cling together, forming larger and larger structures. They contain an enormous variety of complex molecules, including organic compounds. But their chemical composition can shift under the influence of external energy flows. If the resonance grows strong enough, it causes the entire cloud to oscillate, a slow, deep trembling. These cosmic vibrations may compress certain regions, producing small pockets of high density, the very embryos of future stars. Clouds can also interact with each other. Sometimes they collide directly. Sometimes only their edges brush together. Both scenarios can lead to a sudden rise in density, a dramatic compression that sparks the rapid birth of star clusters. But such events are difficult to observe. They unfold across unimaginable distances and over spans of time far longer than a single human lifetime. These variations might arise from magnetic interactions, turbulent flows, or uneven cooling. Rare observations show clouds erupting with sudden bursts of energy, flashes triggered by interactions between particles and magnetic structures. Some clouds contain zones where dust behaves in strange, unexpected ways. Dust grains may become magnetically aligned, forming stable structures that interact with the gas around them, creating dense pockets crucial for the birth of protoplanetary disks. Another important detail is that clouds can possess their own rotation, not uniform, but subtle, appearing only in specific regions. This uneven rotation can shape the gas into zonal patterns, redirecting its movement. These patterns may create areas where matter becomes dense enough to collapse, slowly forming the seed of a future star. Research suggests that clouds may also contain hidden flows of energy. If such hidden streams exist, they could deeply influence the cloud's internal dynamics, subtly reshaping it from within. Among the lesser-known cosmic interactions is a phenomenon that occurs when a cloud passes near a black hole. The cloud may feel the stretching effect of the black hole's intense gravity. Its shape, slowly distorted like soft fabric, drawn toward a whirlpool. Sometimes the cloud breaks apart, forming long streams of matter spiraling toward the black hole, eventually creating an accretion disk. If the skeleton is strong enough, it can survive for ages, even while the cloud is shaped and pushed by external energy streams. There are clouds that display slow-moving pressure waves, drifting through their interior like gentle tides. These waves alter the density of matter over enormous distances and may be triggered by interactions with nearby interstellar structures or external energy flows. Some hypotheses suggest that clouds might help create large-scale structures within galaxies. If a cloud is massive enough, it can alter the distribution of mass in its region, producing gravitational anomalies that influence the motion of surrounding stars, subtly sculpting new shapes within the galactic disk. These rapid transformations may be caused by internal processes, collisions between dense regions, turbulence, or sudden compressions. If such changes indeed occur, they may be crucial to the formation of star clusters and the evolution of entire galactic neighborhoods. Black holes are considered some of the most mysterious beings in the cosmos. They sit in the dark like ancient watchers, drawing in light, time, and every quiet whisper of gravity around them. And even though our understanding of them has grown impressively over the years, there are still countless processes wrapped in darkness, existing just beyond the reach of our instruments and our imagination. And the strange phenomena believed to occur just behind the event horizon. Direct observation is impossible, but gentle, indirect hints let scientists construct hypotheses, whispers that expand our understanding of how black holes shape the architecture of the universe. Although black holes don't possess a surface in the usual sense, they create regions where gravity becomes so intense that even light has no hope of escaping. This invisible boundary is known as the event horizon. And near this frontier, strange things happen, things classical physics cannot easily explain. Particles drift in ways they shouldn't, as if responding to hidden currents or to laws we have yet to discover. One of the lesser-known phenomena is the existence of regions where space becomes so violently curved that streams of energy seem to intensify. These flows may form through the dance between the black hole and its accretion disk, a swirling, glowing ring of dust, gas, and time itself. Inside these disks, matter heats to extraordinary temperatures, glowing with intense radiation, but intriguingly, this radiation is uneven. It flickers, pulses, shifts, as if waves of density move quietly through the disk, stirred by unseen magnetic hands. Some accretion disks appear to have a layered internal structure, almost like a cosmic millefeuille. Each layer carries its own temperature, its own density, its own rhythm of motion. And this creates zones where heating and cooling proceed differently, carving out pockets where dense particles gather into clusters. These clusters can become sources of sudden high-energy burst flashes of light, brief but powerful, like cosmic heartbeats. Some studies suggest that accretion flows can twist into vortices. These swirling currents funnel gas toward the poles of the black hole. If the flow becomes dense enough, it may ignite the formation of jets, narrow, brilliant streams of plasma hurled across space at near-light speed. The inner workings behind these jets remain deeply mysterious. But magnetic fields, ancient, invisible, endlessly patient, are believed to guide and accelerate the plasma. There are moments when black holes behave strangely due to their rotation. A spinning black hole can steal energy from falling matter, amplifying the energy within its surrounding space. But these processes occur right on the edge of the event horizon, where even time behaves differently. Observing them is incredibly difficult. Some theories suggest that rotation itself twists spacetime, creating additional effects, gentle, persistent distortions that alter the trajectories of nearby particles. These distortions may form structures resembling cosmic whirlpools, generating bursts of high-energy light. Research indicates that black holes can possess magnetic fields of their own. Sometimes magnetic fields shape stable structures, long-lasting formations that shine in X-ray wavelengths. There are black holes that show unexpected changes in rotation, speed. They may spin faster as they devour matter or slow down as they lose energy. These shifts influence the surrounding radiation, altering the rhythm of the cosmic environment. A special area of interest involves so-called micro-black holes. Hypothesized to have existed in the early universe, these tiny objects would be incredibly difficult to detect, too small to significantly distort surrounding space. But if they exist, they might influence how mass is distributed across the cosmos. Some research suggests that black holes may evaporate. This evaporation, extremely slow and subtle, is caused by quantum effects at the event horizon. If true, black holes may release gentle streams of energy throughout their lifetime, fading over unimaginable spans of time. There are hypotheses that black holes help sculpt large-scale structures in galaxies. A black hole at the center may direct gas flows, creating zones ripe for star formation. Or, in some cases, suppressing star birth by scattering gas outward. As the disk shifts, it alters particle movement, creating flows that drift silently toward the black hole. Rare observations reveal black holes with unusual shapes. Rotation, nearby objects, or dense disk material may distort the form of the event horizon, making it asymmetric, stretched, or twisted. Some of the processes unfolding near black holes may carry a deeply quantum nature. Quiet, subtle, almost delicate. And if these processes truly exist, they may gently influence the character of the radiation we observe, soft pulses, faint ripples, like the universe breathing in the dark. There is a hypothesis that quantum effects may create structures that resemble slow, rhythmic pulsations. as though spacetime itself is trembling, vibrating in the presence of a black hole. Another fascinating question is whether black holes interact with flows of dark matter. If dark matter drifts close enough to the gravity of a black hole, it may form streams, halos, or even quiet patterns of motion we cannot yet see, only feel through the behavior of surrounding light. But black holes, as mysterious as they are only one small fragment of the cosmic tapestry. The universe is filled with a striking variety of stellar objects, far wider and stranger than what enters our everyday field of view. Stars themselves contain hidden inner processes. Subtle rhythms of plasma, layers of magnetic tension, ancient fires that evolve in ways we still barely understand. Their evolution is filled not only with known stages, but also with rare and little-studied phenomena that have long remained outside traditional observations. These phenomena include unusual forms of energy release, complex magnetic configurations, atypical mechanisms of mass loss, and unique scenarios of interaction with the surrounding environment. Exploring such processes helps us expand our understanding of how stars live, breathe, change, and quietly influence the architecture of the cosmos. Stars are never truly still. Within them, density, temperature, and magnetic flows constantly shift. Even if a star appears steady and calm from afar, its inner structure is in ceaseless motion, layers sliding, pulsing, swirling in a slow cosmic dance. When these layers interact, unusual processes can arise, gentle oscillations that travel through the star's interior across enormous distances. These oscillations redistribute energy, sometimes leading to long-term changes in brightness. One little-known process is the existence of stars with variable layers of activity. Such stars may contain zones where plasma moves along intricate, twisting paths, and these paths create regions where energy builds up quietly over time. Some stars show strange changes in their rotation speed. These shifts may be caused by interactions with massive companions. It is fascinating to observe phenomena occurring in stars at the late stages of their evolution. At these stages, a star expands and its outer layers become less dense and more fragile. As the structure weakens, these layers may detach, peeling away softly into space. Some stars are surrounded by disks made of dust, gas, and solid particles. If such a disk becomes sufficiently dense, it can cast a shadow, a gentle, cool region where temperature distribution shifts. These temperature changes may lead to conditions that allow planets to form. These runaway stars may have been ejected from binary systems. High density may accelerate evolution. Lower density may slow it down. This captured matter may form an accretion disk, and if the disk grows sufficiently massive, resonance zones may appear within it. These shells can be surprisingly intricate, woven with layers of uneven density. When such a shell meets external streams of energy, delicate oscillations may arise. Ripples that drift slowly outward, like expanding circles on a still, dark lake. Some stars possess inner layers that drift independently from one another, almost like silent gears turning in the deep. When these layers touch, they may create waves soft, internal tremors that travel through the star's hidden structure. If dark matter truly interacts with stars, it could subtly guide their evolution. This can lead to spectral fingerprints unlike anything we usually see. Exoplanets can follow orbits that defy classical models. Migration is the gentle drifting of a planet across its system. This is how hot giants are born, massive worlds orbiting so close to their star that their atmospheres are slowly stripped away. Streams of particles peel off the outer layers of these planets. The intense pull of the star can even deform the planet, stretching it subtly along the direction of the starlight. These movements shift pressure and structure, sometimes causing the surface to tremble or pulse. If the surface changes shape, the atmosphere responds as well, swirling, bending, reshaping its winds and climate. Such contrast creates extreme temperature differences, powerful storms, and turbulent, spiraling jets. These clouds reflect starlight, creating unique spectral signatures that reveal their composition. If the surface remains frozen due to low temperatures, liquid water may still lie beneath. Tidal heating can keep these hidden oceans warm and alive. Some planets display unusual patterns of rotation. There are planets with remarkably low density, so puffy and expanded that their radius is large. But their mass is surprisingly small. This may occur when a planet contains vast amounts of light, gases that inflate its atmosphere. Some exoplanets wear rings broad, shimmering structures of dust, ice, or solid particles. These rings can be so expansive that they dim the starlight. If the rings are thick enough, they influence the planet's spectrum. Their shapes may shift over time through interactions with nearby moons or passing bodies. And then there is the question of moons. Some exoplanets may have satellites with atmospheres of their own small worlds that breathe quietly in the distant dark. In some cases, moons may exhibiting a quiet, persistent warmth born from gravitational tension. Vast reservoirs of liquid water, sealed beneath layers of ice, quietly shifting in the dark. If thick clouds swirl through the upper layers and reflect starlight, the planet may shine brighter than expected, almost glowing softly in the cosmic night. Studies suggest that many planets endure sudden, dramatic temperature shifts. For instance, when a highly active star sends torrents of radiation toward its planets, temperature may rise or fall within moments. Such abrupt transitions reshape the atmosphere, bending its currents. It is also important to remember that planets themselves evolve over time. Some exoplanets may be coated in enormous global oceans waters deeper than any found on Earth. Creating a world wrapped in endless waves. Moving heat with slow, hypnotic persistence. Enigmatic shields that interact with their atmospheres. If the magnetic field is strong enough. Visible as strange, soft lights in the spectrum. Another captivating mystery is the origin of some planets. There are worlds that may have formed from the shattered remains signatures of violent histories long past. Even after decades of study, many of their internal processes remain hidden. Their mysteries include deep internal oscillations, interactions of ultradense matter with colossal magnetic fields. One lesser-known phenomenon is internal stratification. The layers inside a neutron star can differ sharply in density. Where these densities shift abruptly, a boundary forms, a kind of inner surface. Waves may ripple along this boundary, spreading outward, influencing the structure of the entire star. Some studies indicate that neutron stars may possess internal magnetic fields, far stronger than anything found in ordinary stars. When these fields interact with hot plasma, magnetic lines can twist and reconnect, releasing bursts of energy, sometimes in powerful flares. Such outbursts may last from fractions of a second to several minutes, their nature still not fully understood. Interestingly, the outer layers of neutron stars can behave like a crystalline lattice, rigid, strong, fragile under immense pressure. When these layers strain past their limit, they crack. This fracture is known as a starquake. A starquake can unleash tremendous amounts of energy, altering the star's rotation in a single moment. Some neutron stars rotate with astonishing speed, hundreds of revolutions per second. These are pulsars. Their rapid spinning flattens the star slightly, changing the shape of its magnetic field. If the magnetic poles shift, their beams of radiation may change direction, altering the pulses we observe from afar. There are neutron stars that lose energy unevenly. Internal disturbances, especially in the superfluid layers, can cause sudden jumps in rotation. These abrupt changes are called glitches. A glitch can be so sharp that it becomes clearly visible in the star's radio signature. Neutron stars may also interact with their surroundings. A star moving through an interstellar cloud can create a shock wave, a bow of compressed gas that heats up as it collides with the star's motion. This heated gas may glow faintly, revealing the star's path. In other cases, the shock forms a sweeping arc, a structure that can stretch across immense distances. Some neutron stars possess unimaginably powerful magnetic fields. These are magnetars. Their magnetic strength surpasses any other known object in the universe. Such fields can stress the star's layers to the breaking point, triggering bursts of energy that flood the surrounding space. In some cases, can dramatically affect its environment. A particularly intriguing possibility lies deep inside regions where exotic particles may exist. Some theories suggest that in the deepest layers, quarks may be set free from their usual bonds, forming dense, unusual states of matter. Transitions between these states could release energy, reshaping the star in ways we scarcely understand. Such processes, they may be rare. Some neutron stars carry unusual spectral signatures, quiet hints in their light, soft fingerprints of what their atmosphere is made of. Sometimes this atmosphere is woven from the lightest elements, almost weightless, and in other cases, it holds heavy ones, dense, ancient, and full of quiet cosmic memory. When the atmosphere is warmed by an external stream of radiation, its spectrum changes. And these subtle shifts can whisper about the hidden processes within the star, as though something deep inside is stirring in its sleep. Particular attention is drawn to binary systems where a neutron star gently pulls matter from its companion. A delicate disk begins to form, warming slowly, glowing softly in the quiet dark. If this disk becomes dense enough, it begins to ripple with instability. Those ripples can erupt into sudden flares, like distant cosmic heartbeats pulsing through the darkness. Some studies suggest that neutron stars may even become sources of gravitational waves. When the stars shape this rise, spreading outward like tremors through the fabric of space itself. If these oscillations grow strong enough, they create waves, barely perceptible, yet powerful enough to reach across galaxies. Neutron stars, too, can change their shape. Quietly, almost imperceptibly, as if adjusting their ancient, cosmic posture. Internal layers, compressed under impossible pressure, shift slowly. A change in shape means a change in rotation. And so, over time, the star gradually loses energy, spinning ever slower like a cosmic top winding down. Some theories propose that within neutrons, stars exist internal flows, moving in complex, twisting paths. These flows interact with magnetic field lines. And when stability breaks, oscillations rise again, quiet but immense. Gas giants are among the most mysterious worlds we know. Their immense atmospheres, their hidden layers, their deep internal rhythms, all unlike anything seen on rocky planets. Though we've studied them for decades, so much remains unseen. Almost everything we know comes from their surface winds, their clouds, their storms, while the true processes lie far below, hidden beneath oceans of gas. Gas giants are built mostly of light elements, hydrogen, helium, but their interiors are anything but simple. Deep within, gas transforms into liquid, reaching densities that defy human intuition. Where density changes abruptly, boundaries form. One of the lesser-known mysteries is the dance of internal flows. When the flow becomes strong enough, it raises toward the surface, forming zones where clouds thicken. Some research suggests gas giants may harbor internal resonances, gentle but powerful vibrations born from layers of different density. Hydrogen, the simplest of all elements, can become metallic under colossal pressure. Many gas giants also carry internal sources of warmth. Their persistence remains one of astronomy's quietest mysteries. Gas giants may also possess exotic magnetic fields shaped by the motion of metallic hydrogen. These magnetic structures can interact with the atmosphere, producing shimmering auroras, cosmic curtains of light. as if each motion takes centuries to decide whether it should continue. Pressure reshapes motion. And there is more. Gas giants are often not alone. These forces create new oscillations, influence the internal layers, and sometimes even alter the temperature deep within. Sometimes these processes lead quietly, almost imperceptibly, to evaporation. Some gas giants may even drift along changing orbits. These shifts occur because of interactions with other celestial bodies, silent gravitational dancers. If the planet moves closer to its star, the temperature rises. Layers warm, storms awaken. There is also a fascinating hypothesis. Dark oceans, dense and immense, pressed by unimaginable pressure. And where boundaries exist, waves rise, echoing through the planet's deep interior, the edges of the observable universe. Those far, unreachable regions beyond our instruments remain some of the most mysterious places in all of cosmology. There is also a hypothesis that beyond our observable horizon lie regions where the physical constants themselves may differ. Perhaps gravity behaves differently. Perhaps dark matter forms unseen structures stretching far beyond what we can measure. If such structures exist, they could influence visible matter, changing the movements of galaxies in quiet, subtle ways. Massive clusters pull it gently aside. Some distant regions may contain streams of energy moving along unusual trajectories, influenced by filaments of dark matter, where these interactions intensify. Galaxies shift in ways that hint at invisible processes. Another hypothesis proposes the existence of topological defects, remnants of the early universe. Cosmic strings are one example, infinitesimally thin, yet incredibly dense structures capable of warping space around them. Their presence could bend the paths of light, though such objects remain extraordinarily difficult to observe. Some models even suggest the universe could contain tunnel-like structures connecting distant regions. Creating anomalies in the cosmic background. These ideas remain speculative, but deeply poetic in their possibility. Shaping the motion of galaxies in ways not predicted by uniform models. Slow, deep vibrations spreading across millions of light years. These oscillations could redistribute matter, forming dense regions where new structures emerge. Among the most enigmatic possibilities are flows of dark energy. If dark energy density changes, so too does the rate of expansion. Perhaps beyond the visible universe lie whole regions that followed a different cosmic story was higher, allowing structures to grow faster, differently. The observable cosmos may be only a small chamber. Temperature and matter behave differently. Even the quietest places, intergalactic voids, hold silent influence. It can affect the paths of galaxies passing near it. Some studies propose the existence of hidden energy flows may contain objects completely invisible to the electromagnetic spectrum, objects too cold, too dense, or composed of matter unlike anything familiar, even though they emit no light. Their gravitational presence quietly influences the motion of surrounding bodies, nudging, bending, guiding, like invisible hands in the dark. Some research suggests that beyond the observable horizon there may exist countless structures, clusters, filaments, voids. A vast architecture extending far beyond what our eyes can trace. These hidden structures may interact with one another, and when they do, gentle oscillations may arise, waves of movement spreading across cosmic distances, subtle tremors in the deep fabric of the universe. Waves that no one can hear, but that shape the cosmos all the same.